In this video, we see this more complexification of the test that I was talking. This I maze, Y maze, where different reward ports exist and they light up in different sequences, random sequences. And the rat knows that there is reward there because he has learned to react to that. And what we have also investigate is to generate the gradients that the rat has access to each system. For example, here the open space gradient, to generate them on real time by, for example, some set of place cells that the rat could have learned by exploring the environment. He could use then this grid cell system or place cell system to compute important features on the environment, for example, like the open space, to navigate through it. Extending then this model towards more complicated ways of achieving a goal, not only this more kind of taxon navigation of chemosensing, like sensing locally the gradient and then reaching this goal. We have also extended the model towards computing paths through a goal location. So we are going to talk now of this generalization of the allostatic control towards being able to reach goals that are not directly reachable by these more kind of simple navigation strategies like the taxon navigation, where we navigate using chemosensing. And we take inspiration from this neurophysiological result of Johnson and Reddish, where they found that the rat, when it's next to a bifurcation point, it exhibits some sweep forwards towards the possible paths that it can take in this bifurcation. And we tried...
excuse me, I have a question.
Yes.
What do we see exactly here?
So we
what
see...
are these colorful pixels?
These are the firing of the place cells, of the different place cells when in real time. So you can see that when it's in the bifurcation point, the firing just gets a bit far away from the actual position of the not very far, because these forward paths have been exhibited only in very short distances, but you can see that the cells representing adjacent positions fire.
Could we please see it again?
Yeah.
I missed it.
So in the bifurcation point, the firing of the adjacent place cells sweeps a bit more far away from the actual position of the rat. So trying to generalize to some process that would be computing some routes in a more complicated way than simply following some chemotaxis in a gradient. We derive a process where combinations of, in this case, these Gaussians that represent place cell positions would be chaining themselves towards a goal position that in the video is switching from time to time in this green star. The idea here is not only that we chain these place cells to arrive towards the goal position, is that some place cells we know that can actively take a particular position, a semantic position inside the whole representation of the rat. So there is this kind of intuition that some place cells can represent particular positions. For example, bifurcations or corners or several different positions. In this case, this is very simply computed, just to make like a proof of concept that we can make it work, by when there is a big change, when you are chaining these random Gaussians that you launch from the position of the rat, when there is a big change in the direction of the chain, of the path, there's some place cells accumulate energy like indicating that they are part of this maybe a bifurcation point. And this happens repeating many times. We can see in these white representations is the accumulation of energy of having changed a lot the direction of your forward paths. Departing from these bifurcations, the algorithm can speed up the search towards the objective because he can restart its search, its paths, from this bifurcation point, from this point of high energy. And in this sense, we acquire something more, that is this concept of abstraction, and the time of resolution of the search becomes more dependent of the number of bifurcations from the objective towards the initial position, and not so to the actual optimal distance that there is from the initial position to the starting point. If we see a plot where we, in the x-axis, we put the shortest path distance computed with a Dijkstra algorithm, an optimal path algorithm, of the initial position to the reward. And here we have every several searches. So the time to get to the target, following this process of accumulating energy of bifurcations and then restarting from the bifurcations, we see that there is a tendency of the majority of searches being on a more kind of linear dependence, and even less from the optimal distance. So that in a certain way, not all the searches, but there is a tendency that of depending more on the number of bifurcations than on the actual optimal distance. In these different figures, we plot the gradients that are used in the algorithm that is presented in the paper in detail. I cannot go now through it. So finally, and for concluding, we have presented this more based reactive control that is based on self-regulation and can then exhibit complex behaviors that emulate the behavior of the rat in different setups. Self-regulation is seen as this more general meta-level control that we call allostatic control, that builds on top of these homeostatic subsystems. And we have extended this model towards also not being able of reaching more complex goals that are not accessible directly from a simple taxon navigation, so some chemotaxis, that is the case only when using the subsystems of the allostatic control, and is able to acquire the sense of abstraction and making the search towards an objective more dependent on the number of bifurcations. So this concept of self-regulation is being now fundamental for introducing inside a bigger cognitive architecture this more drive of motivations for generating behavior. That this candidate has been the distributed adaptive control architecture. So thank you very much, and if you have any question, I will be pleased to answer.